So today's class is in a slightly different format because I'm not speaking. Instead, we have Jonathan, who will show us how to fold screens and also topological structures.
Yeah, so my goal for today is to introduce to you two paradigmatic examples of topological phases of matter, of non-interacting fermion systems. And the reason we're only going to look at fermions is exactly because we're only going to look at non-interacting. And the reason we're only going to look at non-interacting is because when discussing topological classification of phases of matter in 3 hours or less, especially after we had all this shenanigan, one has to be modest, right? Because, and here it's important to explain what this whole topological classification of phases of matter really means, okay? Because initially, when physicists thought about how to classify quantum phases of matter, they thought about it in the same way that you think about classical phases of matter, to classify them using symmetry, okay? So that goes into what we call the Landau paradigm, okay? So, and even in this classical classification, the physics is extremely complicated and rich, right? We can break time versus symmetry and then it's like a ferromagnet, or we can break translational symmetry and then it's a crystal. We can break rotational symmetry and then it's a nematic, and so on and so forth. And even when we just talk about breaking translational symmetry, right? There are so many different types of crystals, so it's very, very rich. Now think about topological classification is something that transcends that. Okay, so we have phases of matter that can have the exact same symmetry, but differ due to some internal topological structure inside the ground state or inside their wave function. So that alone makes it much more rich, and for that reason, we're going to do a very modest thing and just show you two paradigmatic examples of topological phases of matter. But I will say that these examples are extremely important. Like they're initially the first baby step in understanding topological matter are these phases. And the phases that I want to discuss is one, the first one is the Schrieffer-Heeger model, or in short SSH. Okay, and the second one is the Haldane model. Haldane model. On a hexagonal lattice. On hexagonal lattice. Okay? These are the two examples that we're going to look at. This. Yes.
Can you remind us why topological materials are useful?
Well, why are topological materials useful? So first of all, I'm not yet talking exactly about topological materials. I'm talking about topological classification of non-interacting fermionic systems, which means band structures. And if you're asking why it is important, so as I mentioned in the beginning, the first thing is that purely from trying to describe and understand the physics of phases of matter, it is a classification which transcends symmetry, as I explained. So that's first of all to understand it, but it also has physical implications which we will discuss, such as edge states. When you transition from one topological state to another, you will have something similar to a phase transition. So you can have, and all these are observable phenomena again, it's a powerful way to understand. And actually, maybe a good way to answer your question is exactly to start from the first example. So, and explain why this can help us. So the first example is this model by the SSH model was used to understand the physics of. Okay, so I'm not a chemist, neither are you, but still, maybe let me make these chemical drawings, which are very nice. So this is some sort of very soft crystal, organic crystal, that has unusual electronic properties. Okay, so already in the early 80s, people knew that it has both optical, like you could see these both in optics and in just transport. You can make it sometimes conducting. One of the things that was very interesting is that they saw that that you have this kind of alternating bond. So these are carbon bonds, similar to what you have in graphene, which are alternating. And one of the things that was observed is that you can have domain walls, kind of what you call solitons, between this kind of configuration and say the equivalent configuration where, you know, the double bond structure is opposite. So you can have a domain wall between these two structures, and these carry solitons, for example. What?
You didn't draw the domain wall.
No. So a domain wall would be, for example, what happens if. Why are all these? Maybe this is better. A domain wall would be something like this. Okay, so a situation where you have, like I'm not a chemist, I don't know how to explain exactly how that happens, but from the physics perspective, this is like one kind of configuration and this is the other. And in the real material, you can have domain walls between them. And these domain walls, for example, carry charge. And to understand that, like the modern way to understand that, why solitons carry a charge, topological, yes.
Could you explain what is a soliton?
I will not explain what a soliton is, but I can say that a soliton is what we call, typically when we say soliton, we refer to a solution of a nonlinear one-dimensional differential equation that is well localized in space and is conserved. So it's something like a wavefront. If you've ever seen, like in Berger's equation, you can have a wavefront which is propagating like a particle. We call that a soliton. Okay? It's a topological, not topological, it's
actually a very confusing term here because you don't see the soliton when you look at this.
Okay. If you open the literature about polyacetylene and you read the early 80s literature, that's how they refer. Okay? Don't blame me. But that's in any case, we're not going to deal with that. We're going to do non-interacting band structure physics. Okay, so no need to know what solid. Okay, so the idea, so the model is therefore extremely simple. Okay, so similar to graphene, we're going to have electrons hopping between carbon atom sites. We can neglect the hydrogen bonds out here. They're not contributing to us in any way. And then the idea would be that there is some sort of alternating hopping amplitude, which depends on whether this bond is a double bond or a single carbon. Okay, so that's the model that was suggested by these gentlemen. So it would be something like, okay, so first thing, I'm sure you've learned about Bravais lattices. This is not a Bravais lattice, right? The Bravais lattice is actually double because we have a basis with two types of atoms, and we can, for example, name one A and the other B. Okay. So then we would have. So first of all, I'm writing now a Hamiltonian in second quantization. So I understood that some of you do not know. So okay, let me write it down and then we can discuss. So this would be something like Bj plus B dagger J Aj plus 1 plus Hermitian conjugate. Sorry, no. Sorry. A dagger J Bj plus T2 Bj dagger Aj plus 1 plus Hermitian conjugate. What I've written here is exactly the opposite process. The process of hopping, say, from, let's say that this side here is J, then this side is J plus 1, and so on and so forth. So we're describing, and these sides are A, and these sides are B. So this describes the hopping between A and B in the same unit cell, and this describes the hopping between B and A between units. Okay. Now, does anyone have a problem with me writing a Hamiltonian like this? No. So if you, this is your last chance, like in a wedding, to complain.
No, let's do it the other way around. Please raise your hand if you're comfortable with second quantization.
No, but that's.
If you didn't raise your hand, in
although we know he is comfortable with second. Okay. So this is the Hamiltonian. Okay. Yes.
Since the sites different, why don't you include the on-site term?
Okay. So Oz is asking, why isn't there also an on-site potential? Right. We can add here a term which is something like delta A dagger J Aj minus B dagger J Bj, which describes the difference in the potential in the different sites. And the reason we don't add that is because actually each one of these sites is completely identical in the on-site structure. And it doesn't matter if the double bond is to the right or to the left, they have the same energy. But this term will be extremely important for us later. Okay, so this, remember this on-site potential. So now what we do is we transform to Fourier space, as we usually do. So Aj, we write as 1 over n is the number of sites in this lattice. Okay, sum over k e to the I k x j. Okay, and say Bj, I can write as 1 over square root of n. Sum over k. So let's agree that.
Can you write the equation somewhere else, just because the podium blocks it?
I'll write it over there. But let's agree that this distance here is a. Okay. So I'm going to use a. Why not? עד שמצאתי טור שעובד וגם רד לו?
Red is okay.
Let's try with red. You should know all this. So this is a 1 over square root of n, sum over k, e to the I k xj, ak, and same thing, bj is 1 over square root of n, sum over k, e to the I xj, bj, and this xj is just a times j. And here I'm using the gauge or the convention where I do not add the phase difference between the two sites, although they're not on the same site. I can add it. It won't change the physics in any way. Okay? And if I plug this in, our Hamiltonian assumes the form, and I'm writing it now as a matrix in a matrix structure, A dagger K, B dagger K, 0, 0, and here we have minus T1 minus T2 e to the minus IAK, minus T1 minus T2 e to the IKA, and here we have AK, BK. Okay? Is it visible at the back? So this, now you see something very important, which you've already seen probably when you studied graphene, is that the sublattice degree of freedom can act like an effective spin. We call it a pseudo spin, where this matrix is has the structure, right? We can think about this matrix as some sort of some sort of let's assume that we call this guy, I don't know, psi dagger of K. It's like a spinner, and this is psi of K. Then it has the structure of psi dagger of K, some B of K dot sigma psi K. Now, if you don't understand this notation, not a big deal. Okay, you can forget about it. But for those who are familiar with this, what this Hamiltonian really describes is like an effective magnetic field. And the eigenstates of this Hamiltonian are going to be the value of this field plus and minus, just the magnitude. And the direction of the spinners are going to point either along the field or against it. And what you can see in this structure is that as a function of where we are in the Brillouin zone, this direction of the spin is going to change. And we can also easily diagonalize this Hamiltonian or obtain its spectrum, right? Because the spectrum is just the square root of the determinant. So in this case, let me write it here. Epsilon K is plus minus the determinant of this, which is going to be, I think, T1.
T1 squared plus T2 squared plus 2
Yes.
T1 T2 cosine.
Reminder, we saw something very nearly identical with
Okay, so now if I plot this band structure, okay, maybe I'll start erasing stuff because it's becoming too hectic here. So this is the dispersion, and let me also write the eigenvectors, which will be of use to me. So we have U plus of K, which corresponds to the upper band, is 1 over square root of 2, 1 e to the I phi of K, and I'll describe in a moment what this phi of K is. And U minus of K is 1 over square root of 2 e to the I phi K minus 1. Okay, these are the two eigenvectors. Now let me draw the
That
complaints.
that doesn't seem right. 'Cause
Why?
It wouldn't. They're not orthogonal. 'Cause you-
They're not orthogonal.
Or they are.
Why are they not orthogonal?
Well, because look, you do U plus conjugate times U minus. It wouldn't give you 0. It would give you sine.
minus and sine.
Here it should be a minus, right? So now let me draw the dispersion. So epsilon plus minus of K as a function of K looks something like this. It doesn't sound good. It's about to break.
At least there's a warning.
At least it's not the theoreticians. בוא בוא תעזור רגע.
No. I thought.
מה זה התפרק? מה?
אתה מאשים את התיאורטיקה, את האנטי-סמאי.
אבל זה נכון.
זה לא משנה.
זה לא משנה. Okay. I don't think that's...
It doesn't hurt.
From the days I moved apartments, I remember how to do that. Okay, so where was I? Okay, so I'm drawing the dispersion. Very problematic. Okay, so here we have the edges of the Brillouin zone. This is minus pi over a. It's a one-dimensional Brillouin zone. And we have two types of gaps here. The gap here is T1 minus T2 in absolute value. And here at 0, the distance between this point and that point is T1 plus T2. Okay? Now, and the last thing I need to tell you is what is this phi of k. So this phi of k, I hope you can see from over there, is the argument, right? It's the argument of minus T1 minus T2e to the minus iak as we go through this Brillouin zone. Okay? And basically this is like a circle of radius T2, and this is a shift by T1. Okay? So I can think about it like this, right? So minus T1, so let's say this is the complex plane. Okay, so minus T1 is here. Okay, and then we have a circle of radius T2 going around it. So this is T2. And as we go from one side of the Brillouin zone to the other, this thing will wind by 2 pi. So we're basically making this entire circle, maybe in the other direction, probably, right? Sorry, in this direction. So we're kind of winding like that. This is what this phi is really telling us. So if you like, the pseudo spin that we were talking about here, these are these states. Okay, one of them is pointing along this vector, and the other one is pointing against it. So we said no blue, right? No blue. So that means that you see the vector is basically changing like this. So if I make a drawing of the specific situation I just drew, then when we start at 0, the pseudo vector is pointing here, and then as we go around, so let's go around. So we start going around. So it starts to cant like this, maybe, but then it starts going back, right? Going back like here, and maybe going a little bit up, but then just going back. Okay, so this is the way it's winding. On the other hand, you could imagine a second situation, right? Where I'm drawing again. So this, by the way, this is the situation when, you can't see this probably because of it. This guy is the situation when T1 is larger than T2. Is that visible, by the way? But we have a second scenario where T1 is smaller than T2. In this case, it means that the radius of this large circle is actually greater than the distance from the origin. It's going to encompass the origin. So we're going to have a situation like this. Okay? So now, as we wind around, as we go through the Brillouin zone, right? We start here at one end of the Brillouin zone and go all the way around. We're actually going to have this vector is going to point like so. So if I look at how it winds around as I go through the Brillouin zone, then it's going to have a structure that looks, maybe it's going to go a little bit faster here, and then kind of slowish but you see that it's going to make a complete winding. Okay, and this already gives you a taste of the topological distinction between two phases. One where T1 is larger than T2, and then the winding of the pseudo vector basically doesn't wind completely around the circle. It basically starts to wind but then goes back. And another one where it creates a complete winding, and you can convince yourself that there is no it's kind of like a Möbius strip. So, you know, it's a strip, and I'm going to strip in class. Okay? So, you know, you can have the belt close on itself, or you can create one winding in it, right? And these two structures, okay, I cannot deform one into the other. It doesn't matter how many times I spin it around, I'm always going to have one winding in it. The only way to unwind it is to detach it somewhere and then connect it again. And this is exactly the same thing that happens here. There is no way to go from this to that unless we do something severe. And that's exactly what happens when T1 is equal to T2. Because when T1 is equal to T2, these two bands touch, and then the distinction between them becomes vague. And that's what allows us to go from one to the other. Okay, so basically touch at that point. And then you can have, if you like, superposition of these two that would give you any direction you like. Okay, so that's one comment. Okay, so that's kind of, if you like, a very hand-wavy argument. But in the late 80s, so at this stage, so the polyacetylene was, the Suschreiter-Wigger model is the beginning of the 80s. But somewhere in the mid-80s, Barry introduced his phase, and Yoshua Zak from the Technion identified that one can use this understanding to say something interesting about the polyacetylene problem. And he proposed what is known as, wait, did I want to comment something? No. Okay. Which is known as the Zak phase. So this is a type of, or a version of Barry phase, which Zak proposed to characterize these bands. So let's see that. So the definition of this Zak phase is an integral over the Brillouin zone, dk. So we go through this Brillouin zone. Isn't there an I here? Oh, you're missing it. Yeah. C minus I, and then we have let's write U eta of K dagger dk U eta of K. Okay, so this is the definition of this Zak phase, and we can calculate it directly using the vectors. Maybe I'll write the vectors. Let me write the vectors again here. So we have U plus of K was 1 over square root of 2 1 and e to the I phi k. And the other guy, U minus of K, was 1 over square root of 2 e to the minus I phi k and minus. Okay, so we can, for each one of these bands, we can characterize them using these guys by just plugging them in here, computing the derivative by k. So this, for example, if I compute it for the minus guy, then this guy is going to fall under the derivative, and then they're just going to multiply each other. And you can see that the only thing I get is just this phi k. So what I really get out of, in this case, is I get an integral from minus pi over a to pi over a dk phi k dk, which, as I say in It's the best kind of integral, like the easiest type of integral in the world. It's a complete derivative. So it's basically just a phi of pi over a minus phi of minus pi over a divided by 2. Okay? Sorry, there's a 1/2 here. 1/2. This 1/2 is super important. This 1/2 comes from this 1 over square root of 2. And the origin of this 1/2 is the fact that the phase here, this phi k, is a relative phase between the sublattices. And we're going to see that in a moment. That's like super important. Now, what you get here is a situation where you have 0, eta equal to -1. Okay, so we're going to focus only, so I'm going to look at the situation where the chemical potential is here, and therefore I want to know only the topological invariant of the lower band. Okay, so you can ask why that's important. The reason is because when we have a fermionic system, you know that you fill only the states at the ground state. We fill only the states that are below the Fermi energy. And remember that the name of the game here is to classify ground states. So we have something like a Slater determinant where we occupy all the bands below the chemical potential. Okay, and the chemical potential, we can play with it. We will play with it in a moment. So I will put it here, here, and here. But for now, let's put it in the middle. And then we only want the topological invariant of the minus band. Okay? Although this result doesn't depend on the band. Notice that both bands will give this result. Okay? And then we have 0 if T1 is larger than T2. Okay? And pi if T1 is smaller than T2. Okay? And this is our topological invariant. Now let's discuss this topological invariant. There are a few comments we need to make. But first, are there any questions?
Let's stop the question.
Yes.
But why? Like, why would you just ask for the phase?
But why would you ask for the phase?
Like, I know.
So
how
Yoshua
Zapp
Zapp, again, Yoshua Zapp came to it
Yeah.
from the perspective of a Berry phase. He imagined that he has a wave function, like a single particle wave function. So the idea behind the Berry phase, I don't know if you've been...
It's usually done for adiabatic processes.
Exactly.
This isn't an adiabatic. It's
Exactly.
a field. It's a multiple
Exactly.
constant.
So, okay, that's the,
No, but
you know.
please remind those who don't know.
Okay, I will. So when you studied adiabatic theory in quantum mechanics, the idea was to look at the wave functions of a Hamiltonian that is changing very, very slowly in time. The idea, when we say slowly, what we mean is that all the state that we start from is separated from all other states by gaps, and the rate at which we're changing Hamiltonian is slow compared to these gaps everywhere. And when you do that, you can avoid hopping or tunneling, if you like, between these different states. And then the wave function can be, and this is a whole formalism in quantum mechanics. And before Berry, okay, what physicists always taught in class or thought, whatever, is that the phase that you acquire as you change, the Hamiltonian, the wave function is just a dynamical phase that you can gauge away. It's like a global phase that doesn't, it's not important for anything. But Berry identified that when you have topological structures in the Hamiltonian, okay, then there are pieces to this phase that you cannot gauge. Okay, so this is, I'm not going to get into those details. This is what they call Berry phase. As you mentioned, the idea, at least the original problem that Berry was looking at, was the wave function on in a triangular well, where he changes the distances between the, like, it was a problem of like solving, you imagine that this is like a well, and he's changing these distances between the triangles as a function of time. And he saw that sometimes when he does a complete circle, the wave function goes to minus itself and not to plus itself. And, initially people thought he was sure that it's some artifact or something like that. Eventually he understood the physics behind it. But that is dynamical. Here, and this, if you like, this is Zach's brilliance, right? Because Zach said, okay, I can think about this K as a dynamical problem. Like I'm shifting an equivalence to the dynamical problem. Now, if you want a way to think about it, is that you know that according to Bloch theorem, if you put an electric field, the states are actually going to sweep through this thing. So, for example, if you put this system in an electric field, then all the wave functions are going to wind again and again and again. If you do it adiabatic compared to this gap. So you can do dynamical processes that will probe this very thing. But the beauty of it is that you can let go of that and just identify that this invariant distinguishes between two types of band structure. They're not the same. One of them has this topological winding in its band structure, and the other one doesn't. And for now, it doesn't tell you anything. It doesn't give you anything. But in a moment, I will show you that it has physical consequences. Okay? Any other questions? Okay, so, but there is a problem here.
Can you maybe just define the term topological constant?
No, a topological
Invariant, sorry.
A topological invariant. First of all, okay, there is no easy way around this. Like you need to gain intuition. Okay, we will have to play with it and understand. But what you see here is basically a mapping from a circle to a circle. Okay, one circle is the Brillouin zone, and the other circle is where in space does this spinner point. Okay, and topology is a field in math that deals with structures, how to quantify a global structures. Like the most famous example would be like the number of holes, or what they call a genus, all sorts of stuff like that. One of the things that topology deals with is mappings. Okay, so, and here you can see a very nice example, which is very obvious, like the Mobius strip, that when you go from a circle to a circle, there is what we call a Z topological invariant, which is the number of times you wrap around the circle when you do one circuit around this Brillouin zone. So when you go around the Brillouin zone, you can have a situation where you stay all the time the same. You can have a situation where you wind once. You can have a situation where you wind many times. Okay, so and that's like what we call a Z topological invariant. Very trivial thing, and here we see it showing up. If we would divide this phase by pi, we would exactly get 0 for the trivial phase, what we call trivial, and 1 for the topological phase. And the whole idea behind the topology is that this invariant is an integer. And the fact that it's an integer is extremely important because it means that it cannot change continuously, right? You cannot change from 0 to 1 in a continuous manner. It has to be an abrupt change. Okay, so that means that this whole topological classification is something that it doesn't depend so much on microscopic small details, but if you can classify your phase, it'll be either 0 or 1. Okay, these are the only two things that you can have. Okay, but I don't want to say much more than that because we will see in a moment more examples. But I do want to say something very, very important, that we do have a problem. I am expecting some sort of question from the audience or a complaint, but to trigger that complaint, let me compute this Zach phase in two other situations. So first of all, if I put the chemical potential here, okay, then both bands are empty. You know, I obviously get 0. But what happens if I put the chemical potential here? Okay, if I put the chemical potential here, then I actually have to add both Zach phases. You know, both of the top band and the bottom band, and you see that they both contribute pi. So if mu is greater than say T1 plus T2, then we have that phi z is going to be something like phi z of plus phi z minus, and in that case we get we get 2 pi. Sorry, let's write it the same way we did before. We get 2 pi if T1 is smaller than T2, and 0 if T1 is greater than T2. And then you could naively say, okay, that's good, because it implies that we still have this topological classification, just that each band contributes 1, and here we have, this is like 2 windings. Okay? And naively you could think that, like I said before, because in topological, in math, the mapping from the circle to the circle is a z invariant. It's how many times it wraps. You could also think that the Zach phase is a z topological classification. Like it can be any integer number of windings. But this actually turns out to be false. It turns out that in this case there's actually only 2 configurations, topological and trivial. So what we call a Z2 topological invariant. It can only take 2 values. And now what I want to explain is how can we see this. And the idea would be that you have to remember that when choosing these wave functions, we actually have gauge freedom. We can choose them any way we want, right? The only condition is that they are eigenvectors, orthogonal eigenvectors of the Hamiltonian k at each k. So that means that I can add, for each one of them, I can add a phase, e to the I theta plus of k, and e to the I theta minus of k. I can always add this phase. It will not change. They are still eigenvectors of this Hamiltonian. And when I do that, what I will find is if I compute the same Zach phase for each one of the bands. So the only condition, by the way, the only condition that I have is that we need this phase to be smooth. Okay? So that means that it needs to have the same periodicity of Bloch states. Okay? So that means that theta plus minus of k plus, I don't know, pi a has to be theta plus minus of k plus 2 pi L, and where L is an integer. So that's a condition for the periodicity of the Bloch states. And if I plug these states now into the same calculation, you see that I'm going to have exactly the same thing. This global phase is going to go down from the exponent. But the difference is that now it's not a relative phase, it's a global phase. So for both of them, I'm going to get this contribution. And then you can convince yourself that the Zach phase that you're going to get in this case for each one of the eta bands is going to be, again, it's going to be phi of pi over 2 minus phi of minus pi over 2 divided by 2 plus this 2 pi L plus minus. So let's assume, plus minus. So let's call this L eta. So now each band, I can give it a different integer of my choice. I can choose any gauge transformation I want. And this gauge transformation will be characterized by some winding L. Okay, and because it's a global phase, now I don't have this half here. So it always gives me a full 2 pi shift. What that implies, it implies that the 0 configuration can be mapped to the 2 pi, 4 pi, 6 pi, and any multiple of 2 pi that you want using a global gauge transformation. So that means that the only two distinct phases are 0 and pi, because I cannot gauge transform them one into the other. But like 0, 2 pi, 4 pi, I can map into each other, and pi, 3 pi, 5 pi, and so on and so forth. So this is an important comment. Another comment I want to make, there are two important comments we want to make, is, so now we can identify basically this phase as trivial and this phase as topological. Okay? And now I want to make two more important comments. Now I'll erase this finally. Two important comments. The first one regards what, you have a question?
Mm-hmm.
Yes.
Why is the symmetry K plus pi over A in the theta plus
Why is the what?
Why is it theta K plus?
Are you asking about this?
Yes.
Because
Why
these
is-
are block bands.
Y
Okay.
plus pi over A. Why not 2 pi
What?
over A, right?
What?
That's right. It should be 2 pi over
Should be 2 pi over A.
2 pi over A. No. 2 pi over A. Ah, yeah, right. Thanks. Good. So what I want to talk about now is two important comments. The first one corresponds to what Oz was discussing before. What happens if we introduce to the Hamiltonian, okay? So our Hamiltonian becomes this SSH model plus some delta H, where delta H is, I don't know, something like lambda delta minus delta, okay? This is this on-site potential. It means that the two carbon atoms are no longer equivalent, and it breaks this a sublattice symmetry. Yes?
And how is it possible, like in the lab, to do this?
I don't know. I'm just discussing
Okay.
discussing what happens if we do that. We know, for example, in graphene you can place graphene on HBN, and that's a way to do it because H
We'll
and
talk
BN
about it later.
are not the same atom on the two sublattices. In polyacetylene, it would be, of course, much more difficult
It's
because
the same atom.
because it's it's in the end it's like a 3D material made of weakly coupled wires. So there is no way to access them. But I'm just mentioning as a matter of principle. Yes.
Just forget about polyacetylene. It's just an example to make chemists like you. Any two quantum dot-like systems, anything you can describe as binding model where you have a long bond, short bond, long bond, short bond, is an SSH model. So it can be optical waveguides where you can actually make them do this controllably. It can be real quantum dots, like in semiconductors. There's like many experimental examples because this is really the simplest topological model, or let's say borderline topological model.
Well, it's
you can
topological.
get.
It's
I've
a
heard
symmetry
people
protected.
argue about that. I'm saying it's like it's the
Because
simplest model, which is
the
which has-
sublattice is in real space.
Yeah.
But okay, so back to our story. If we add this kind of potential, what is going to happen? Imagine that you have okay, let me draw them again. So imagine that we have these two configurations. One where the spins, kind of almost wind, but don't end up winding, and the other one where they do wind, like say once. Okay, and we argued that these two configurations cannot be continuously deformed one into the other. Like with a belt, you have to rip it somehow and rotate. Okay, there is no a continuous way to do that. But if you add this potential, you can, right? Because imagine what happens if I can't, right? What this describes is that, remember that the Hamiltonian we're talking about, or I erased it, it's like an effective magnetic field. And this term is like a magnetic field that is no longer in the plane. It's pointing out of the plane. So it will cause these pseudo spins to cant out of the plane. So imagine that I kind of polarize them out of the plane, and then I can, kind of continuously imagine a situation where I rotate them like this, okay, without creating anything abrupt or dramatic. And a second thing I want to comment is that if we look at the band structure, remember that if I plot again the band structure here, then we said that this gap here is T1 minus T2. Okay? That means that at the topological transition, when I switch from between these two types of behaviors, the gap actually closes. So maybe I'll make it in a different color. So the situation where we have T1 equal to T2, the two bands touch, okay? And then we have this transition. So what did I want to say about this? So the first comment I want to make is that we see here something that is very common in topological classification, that when you go from one phase, one topological class to another topological class, the gap closes. So that's one important comment. Yeah, what did I also want to say?
I mean, in this case, it's actually just the same band, just shifted upwards in energy by, because this is like your edge of the Brillouin zone, and shifted to the right by half of the Brillouin zone.
No, what you want to say is that when T1 is equal to T2,
yes,
this division into two sublattices is redundant or artificial because they're just the same. And you can think about this branch as actually being the continuation of this branch, and this branch being the continuation of this branch. But that's not what I wanted to say. I wanted to say something, I don't remember. So, okay, so first of all, we see that that breaking a symmetry, breaking the sublattice symmetry, actually allows us to deform. And you can also check that if you add this, I know what I wanted to add. Okay, sorry. So we saw that the sublattice symmetry can actually take us continuously from one configuration to the other, and you can actually check. You can do the same exercise with this kind of potential, and you'll find that there is no longer this sharp classification. It's not 0 or pi. As you strengthen this thing, you can go to a situation where these take continuous values and you can make them equivalent. So the distinction no longer exists. And you can also see this from the sublattice breaking, because what happens is that when you add this delta, then instead of the topological transition being identified with a crossing, a point where the two bands touch, you will actually develop a small gap here, which is 2 delta. So this, actually this is also 2, to be honest. But never mind, but the point what I'm trying to make is that when you add this potential, you also see that this, the fact that at T1 equal to T2 the bands touch is also a phenomenon that disappears. So the topological transition, we now see 2 important things. One of them is that this topological phase is protected by a symmetry. The symmetry is the sublattice symmetry. And if we break that symmetry, then both the topological invariant ceases to be a sharp integer, and also the gap closing between the two phases disappears. Okay, so it develops a gap. And so this is very important because it tells us that if we break the symmetry that protects this topological classification, then there is no longer a sharp phase transition between the two phases, which is associated with a gap closing. We need to take a break now, or
we can
Okay.
Whatever you want.
So no, because okay. So maybe let's finish with SSH
Yeah,
before the break.
So I'll just make the opposite comment that if you don't break sublattice symmetry,
Yes.
your system is very robust. So if you add, for example, some disorder potential,
Yeah.
which is much larger than the unit cell, okay, so it look like, so it doesn't break the sublattice symmetry. It acts the same way on both sides. Your system will be relatively impervious to this potential pervious compared to systems which are not topologically protected. So you still have the same edge states, for example.
Okay. So let's talk about edge states now.
Which is the next topic.
Yeah.
I was giving you a
I was anticipating. So the next topic is edge states. So another property of topological phases is that they are typically characterized by edge states. Now, because this is the SSH model, it's zero energy, let's call it. Zero energy edge states. So now what we need to do is we need to define our basic unit cell because it will be important. So I assume that I always have an integer number of lattice sites. Okay, it means that the end of this chain is going to look like this. Okay.
No.
So the last site looks like this.
No, that doesn't. Oh wait. Oh, wait. Oh, okay.
It doesn't really matter. To be honest, it doesn't really matter. Okay, but I'm going to assume that this lattice is constructed out of these double bonds, and then they're bonded with these single bonds. Okay, so we're going to have an integer number of these structures. So that's important for our edge state analysis. So this is like site 1, this is site 2, and this is site n for us. Now we can write the Schrödinger equation. In the general case, for our Hamiltonian, it's H psi is equal to E psi. And let's say psi is, for example, a Fock state on the different lattice sites. So we can write psi as something like sum over j equal 1 to n, something like alpha j at site aj plus beta j at site bj. So this aj, for example, what I mean is like a dagger j on the vacuum at that site. Okay, so this means that site aj is occupied, or something like that. Okay, and this is like a single particle state, just a single particle state, and these are the weights of it being in all sorts of sites. Okay, it's not something complicated. I'm not doing anything like many body Slater determinants or anything like that. Okay.
Can you write it as a tensor product?
No, that's exactly what I don't want to do. You can think about each one of these guys as a tensor product of empty on each side and 1 at aj. Okay? So it's single particle states. It's just a vector. If you like, it's like a vector where imagine that on each site I have the two sublattices. So it would be something like alpha 1. So let's say this is site 1, this is alpha 1, beta 1. This is alpha 2, beta 2. It's just a vector like that. Okay? That's all I'm doing. And then I can write the Schrödinger equation in terms of these alpha and beta states. It's going to be minus T1 beta j minus T2 beta j minus 1 equals to E alpha j, and same thing minus T2 alpha j plus 1 minus t1 alpha j equals to e beta j. Okay, so I just applied the Hamiltonian we had before in real space on this vector, and then I get equations for these weights alpha and beta. Now I want to search for zero energy states, so I'll equate both equations to 0. Okay, and what you immediately find from these two equations is the following condition, that beta j minus 1 is equal to minus t1 over t2 beta j, and that alpha j plus 1 is equal to minus t1 over t2 alpha j. So this is like a receding formula, and this is how do you call it? The opposite of receding. I don't know. Whatever. But here, this is why it was important for me to do it like this, because you see, this is beta j. This is like beta 1. And this is like beta n. Okay? And this is alpha 1. And this is alpha n. So the point is that you can see here that both of these solutions, they support an exponentially decaying solution with zero energy. Why? Because you could imagine, for example, let's look at alpha. Let's start from alpha. Let's say I want to draw this alpha j as a function of j. So here I have 1, 2, 3, 4, and so on. So let's say I give it some initial weight alpha 0 here. Then at this site, it's going to be, right, it's going to be minus alpha 0 t1 over t2, assuming that t1 is larger than t2. Okay? And then at the next site, it's going to be like this. So it's kind of decaying exponentially and oscillating between site to site. Now, if t2 would be larger than t1, then it would explode exponentially, and I wouldn't find such a solution. Okay? I can only find the solution if I can only find, let's call it a normalizable solution, if t1 is smaller than t2. And I also see that for the beta j, I have the exact same solution on the other side. Okay? Now, there's a very simple intuitive picture for what these edge states really are. Because let's take the limit where we take t2 to be much, much larger than t1, or vice versa. So remember that the hopping parameter here is t1, and here it's t2. So if t2 is much, much larger than t1, you can think about it as a potential well. So let's think of a crystal with potential wells that look like, so t2 is much larger than t1. So that would mean that we have something like a very large barrier, a small barrier, a very large barrier, a small barrier. And then the hopping here is t1, and the hopping here is t2. So t2 is much larger than t1 because the barrier is much smaller. Okay? Then in this situation, what will happen is that the particles will create a superposition in this well if the filling is exactly 1 per 2 sites, which is exactly 1 per site, or 1 per 2 atoms. Remember that we have 2 atoms in the unit set. And in this situation, we see that we have here, at this end, we have a free particle. So basically, it's kind of bonding like this. Okay? And then we have these 2 states here at the end, which are edge states. On the other hand, if we have the opposite picture, let's say that this is site A and this is site B, or before I denoted them by capital A and capital B. We have the opposite picture, which is something like, okay, where this is A and this is B. Then our dimers will be here, okay? which is the other dimerization, where we have dimerization like this, and we don't have a particle at the end. So what we see again now is that this distinction, this topological distinction, actually has a physical consequence. If we cut the system, we have edges to the system, then the two topological classes differ by one of them having zero energy states that are localized on the boundary, and the other doesn't. And this brings us back to the original picture, which experimentalists didn't understand when they studied the electronic properties of polyacetylene, is why do they have these zero energy states that are below the gap that are associated with these solitons, right? Remember you were asking about solitons, right? So this is the explanation for that. And maybe the last comment I'd like to make.
By the way, just notice, this wasn't explicitly stated, but notice that especially for T1, T2, which are sort of similar, this is just an exponential decay of the amplitude.
It is, because the amplitude here is T1 over T2 squared, and the amplitude here is T1 over T2 cubed. And in general, at a certain distance, it's T1 over T2 to the power of, like, I don't know, like n sites, which is like, right, it's E to the minus log, yeah, n log of T1 over, or T2 over T1, or I don't know. Oh, yeah, whatever.
Yeah.
Okay? So this gives us this exponential decay, but I don't know if there's going to be an exercise or something.
Yeah.
There will be an exercise. So in the exercise, one of the exercises I'll give you is to actually write the 2x2 Hamiltonian and change the this parameter T1 minus T2 continuously, and we will see that also there you can just solve like a Schrodinger equation like you had when you did your undergrad. You had these basic courses to solve, Schrodinger equation in a potential well or whatever, and we will see that such a mass change supports what is known as a Rabi-Jacqui state, which was also identified at high energy physics. If you take a Dirac spectrum and the mass changes sign as a function of position in space, then you get zero energy solutions. This is exactly the same thing, and we will see it also from that point. Okay? So it means that when we change from one topological class to another, okay, we get a bound state between the two topological classes. The difference between the two pictures is that here we had a finite chain, and then the edges were, when we're thinking about edges, and when you'll do these Jacqui-Rabi solutions, what you'll actually have in mind is a boundary between trivial and topological phases. But they're actually the same, because that's why we associate the trivial as trivial, because it can be continuously deformed into the vacuum. And by the way, also here you can understand this picture of deforming into the vacuum, because imagine now that we continuously kind of separate these sites from one another, keeping, again, remember that this is a site. This is a site. It's like a molecule or something. We start separating these molecules. Eventually, this T2 will have to become smaller at some point than T1 because we make them farther and farther apart. What I'm talking about is, imagine that I start separating them in space, okay, and I take them to what we call the atomic limit, where I separate them from each other. I have to go through a topological transition. On the other hand, if I have this dimerization to begin with, I can just separate them continuously and go to the vacuum limit without any band crossing or edge states or any funny stuff like that. Okay, and the last thing I want to discuss is actually to connect this model to graphene. Okay?
Maybe we do this after break.
Maybe we do this after. Where is the... So this is something that Hanan asked me to show you guys. To be honest, I wasn't aware of it even. but it turns out that it's quite simple. So I understand that you already saw the tight binding Hamiltonian of graphene. So now let's imagine that instead of an infinite sheet of graphene, we have a graphene with an edge. It's called a zigzag edge. There are two ways to kind of terminate graphene. And so what we're going to imagine is that this is the A and B sublattice of graphene. Okay? And then, as you know, graphene is a triangular lattice of these A and B sublattices. So imagine that we have an edge of graphene that looks like this. Okay? And then I have more graphene in the bulk. Okay? So I hope this is kind of clear. This is graphene. And then you create the graphene by making these bonds. These are hexagonal lattices. But this is the edge of the sample. So here it terminates. Here it continues into the bulk. And then we can define like three vectors. Let's call this delta 1, delta 2, delta 3. Okay, and our tight binding Hamiltonian, right, is minus t sum over side j, a dagger j bj plus Hermitian conjugate. Very simple and similar to what we had before. Now the point is, let me take each one of these zigzag chains and denote them by an index n. So basically this index j, okay, it's basically an mn index, right? Because it tells us where we are in y and where we are in x. So let's say m is x and n is the index for y. So then we can call this, I don't know, like n equal 1, n equal 2, and so on. And I can Fourier transform the x direction, as you did in class. And if I do that, you notice that this guy is completely along x. But these guys, they actually have a y dependence as well. And also you can notice that delta 2 and delta 3, so delta 2 connects the same chain n. So each chain like this is an n. Okay? So the delta 2 connects n to itself on adjacent side, but delta 3 connects between chains. Yeah, and I also remind you that delta 1 is A1, 0. Delta 2 is 1 A over 2 1/2 square root of 3, 1 square root of 3, and delta 3 is A over 2 minus 1 minus square root of 3. And after all this talk, the Hamiltonian assumes the form minus t sum over kx. Kx is a good quantum number, so I Fourier transform. But then I also have a sum over this n, this index of the depth inside the thing. And then I get e to the I kx delta 1x plus e to the I kx delta 3x b dagger kn akn plus e to the I kx delta 2x bkn plus 1 akn, and then this whole thing is plus Hermitian conjugate. Okay? Okay, so to get an intuition where this came from, so remember that delta 2 and delta 1. Maybe I had a different notation. Delta. Okay. In my notation in my notes, it was the other way around. So delta 2 is the one that connects between n and n plus 1, and delta 3 and delta 1 are both within the same n. So then we have this. Both of them connect B sites to A sites, and the phase factors come from the projection of k along x, because we're only doing a Fourier transform along x. Okay, so when I write delta 1x, that's like the x component of these vectors. And now you can already identify that this thing looks exactly like the it looks exactly like the SSH model, right? Because I can rewrite this as I can think about this model as a hopping model between sites n and n plus 1, right? Right, this is the remember that the model that we had before was something like this, and then like this. So here we had, say, hopping T1, and here we had hopping T2, and then the Hamiltonian was A dagger K, A dagger N, let's call it now A dagger N, Bn plus B dagger N, An plus 1 plus Hermitian conjugate. That's how we wrote it before, minus T. This was our SSH model. Okay, and here you can see that we have the same structure. There's an on-site term, but between the sublattices and between sites. Yes, you have a question?
The second term, shouldn't there be a dagger over the B?
Yes. Of course. Otherwise, we wouldn't have conservation of number of parts. Okay, so what we conclude from this Hamiltonian is that in this SSH model, T1 is basically T e to the ikxa plus e to the minus ikxa over 2. And that T2 is T e to the minus ikxa over 2. And then as before, okay, now I'll erase these guys. Now as before, we have that T1 over T2 is equal to 2 times the absolute value of cos 3kxa over 4. Okay? Which implies that as we go through one direction of the Brillouin zone, okay, the x direction, so this is kx, then right, then we have the value 1, so like the value 1, right? And then we have something like this. Okay? And in this region here,
What's the y-axis?
the y-axis is this thing. So it's the ratio, the absolute ratio between T1 and T2. So when T1 becomes smaller than T2, which are these two regions here, okay, then we get a topological phase. So if you like, these regions here are topological. Okay? And the values here happen to be 4 pi over 9a and 8 pi over 9. Okay? So what this implies, it implies that, so what basically what we're doing, remember, we're Fourier transforming along x, and we're basically converting this to an effective SSH model along this direction. Okay, so it would look something like this. So this is like n equal 1, n equal 2, and so on. And what we found is that there is a whole continuum of edge states that are associated with the k states in between these two things. So if we would make it also finite in x, then the dispersion here would become quantized, and we would have a bunch of finite number of states. But if you take this chain to infinity, you're going to have an infinite of these edge states, and they're completely flat. Now, as far as I understand, if you take into account higher order corrections, they develop some sort of dispersion. But yeah, I guess that's all I have to say about these. Okay, so you should know that if you terminate graphene along the zigzag direction, unlike the other direction, then you should expect these kind of edge states to exist. Also, nothing protects them from mixing with I don't think I have anything more intelligent to say. Okay, so this is a connection with graphene, which brings us in perfect position to discuss the second example of topological physics of matter I wanted to discuss, which is the Haldane model. So you know that in 2016, Duncan Haldane won the Nobel Prize together with yeah, maybe someone knows, no? So with Kosterlitz, Thouless, and Thouless and Kosterlitz, okay? And one of the reasons he won the prize, I think that two papers contributed more than anything. One of them is the model we're going to see in a moment, and the other one is a very important conjecture that he made for spin one-dimensional chains. So if you're interested in that, that is a topological phase of matter that is not described by fermions, but by a spin one chain. These are degrees of freedom that don't even have statistics because they're kind of fixed in space. They're not even moving about. Example. Okay. So the Haldane model. So what it's based on graphene. So as before, we're going to have graphene. No.
Yeah. You need to practice drawing graphene.
Yeah. sorry, I forgot there's another atom. I consider myself to be pretty good in drawing graphene.
I'm sure you do.
So we have something like that. And the idea would be, of course, we have this hopping parameter t, but we will also add another hopping parameter, which instead of hopping to nearest neighbor is the hopping to the next nearest neighbor, which we will denote by t prime. And then there is a third element, there is a third element we want to add, which is fluxes. So the way it works is something like this. Here you can see a nice Magen David. And through each one of these triangles here, we're going to pierce flux phi. And through the center here, we're going to pierce a flux which is minus 6 phi. So the idea that Haldane had was that this is a model that you break time versus symmetry because there are fluxes here. And if I would take the equivalent state, which is time versus invariant, then I would have 6 phi in the center and these phi's would become minus phi. But the overall average of flux in the unit cell is 0. Okay? And now, if you remember, we had these 3 vectors. So we're going to call, say, this is delta 1, this is delta 2, and this is, say, delta 3. But then we also define the nearest neighbor vector as gamma 1 is like delta 2 minus delta 3. Gamma 2, whatever I wrote here, I don't know. Gamma 2 is delta 2 minus delta 1, and gamma 3 is delta 1 minus delta 3. Okay, which gives us, at least one of these triangles for the hopping to the next nearest neighbor. And okay, and then the last ingredient that Haldane added is also an on-site potential. So let's imagine, Hanan can't see blue, but you guys can. So imagine that if this is like A and this is B, then he's going to put a different potential on A and B, as we've discussed before. So if I summarize all of these ingredients in a Hamiltonian, so I hope you won't make me write the real space Hamiltonian because it's messy and disgusting. Let me write the momentum space Hamiltonian, and then if you guys, so the Hamiltonian that we get for this model is something like A dagger K, B dagger K, and we have a matrix, and we have A, K, B, K. And then here we have M is the on-site potential, minus 2t prime, sum over J, cos K dot gamma, J, plus phi. I'll explain to you in a moment why it's plus phi. Here we have minus M minus 2t prime, sum over J, cos of K dot gamma J minus phi. And here we have what you already know from graphene. J is equal, J runs from 1 to 3, okay, in all cases. Minus T e to the I K dot delta. And here we have minus T sum over J e to the minus I K delta. This is our Hamiltonian. The only thing that you will probably be confused about is this phi here. Okay? So the idea is that, remember that this block is like A. So it's hopping from A to A. Okay? So let's inflate this for a moment. So this is A, this is A. Sorry, no. This is A. No, תפסיק לצחוק עליי, מה? נראה אותך מה שנקרא. Okay. So if I'm doing this hopping, so I imagine hopping in these directions like this. Okay? Then you see that I have phi, and phi. So that gives me wait a second. Wait, why did I say that it's just phi? Hold on. Yes, okay. So the point is that what you see is that when I make like 3 hoppings, say I hop from here to here to here, I need to collect a total flux of 3 phi, right? And there are 3 hoppings. So one way to, like a gauge, if you like, choice of presenting these fluxes, here I have minus 6 phi, is to make this hopping matrix element, for example, T prime, and then e to the I. So which gamma, let's see which gamma this is. So this is this guy. So it's minus. So it's delta. It's minus delta 3 plus delta 1. Gamma 3. So it's I gamma 3 dot k. But then I want to have here one minus I phi. Why minus I phi? Because the total flux I collect here is minus 3. Okay, for example, I add it like this. And then this guy the same, just with a different gamma, and this guy the same with a different gamma. And then the complex conjugate of that will give me this. And you can convince yourself that if you do the same game for this triangle, then you're going to have the exact same structure, just with the opposite phi. And it might be that here it should be minus phi and here it should be plus phi. Like, don't be Katnunian with me. Okay, but that's not what's important. So this is the model that we get. Okay, and as before, okay, I want to make an important comment. Before we talked about the SSH model, which gives us a Z2 classification in one dimension, and it was protected by sublattice symmetry, also known as chiral symmetry. You'll hear sometimes people call it chiral symmetry. It's the same deal. Here you could ask the same thing, like what symmetries do we have? And first of all, we're going to see in a moment that here the classification is not Z2, it's going to be Z. And this is exactly equivalent to the quantum Hall state. Okay, so if you know, like quantum Hall levels, they can, you have 1, 2, 3, you can have any integer. And here the classification is going to be the same. You can ask which symmetries do I need here? And the answer is actually none. So why? Because notice that M breaks the inversion symmetry and phi breaks time reversal symmetry. So we're left with no M breaks both inversion and the sublattice. So we don't have any symmetries. Okay.
What about like Keith symmetry, maybe inversion and time reversal symmetry together? Those are not necessarily broken, right?
You're asking. Okay, first of all, I didn't think about that, but I don't think that would help. Because M, for example, is not something you can compensate for with another symmetry.
No. So inversion you can apply inversion.
No, but he was talking about constructing a symmetry on symmetry, like inversion times time reversal.
Yes, exactly.
But inversion times time reversal doesn't bring you back the same. Okay. Now, as before, we can interpret this whole Hamiltonian. Okay, this whole thing as like some effective magnetic field dot sigma. Okay, and or if you like, actually that's not true. So what we can say, okay, what we can say is that this thing I can write it as psi of k times identity 2 by 2 plus a vector d of k dot sigma. Okay, where d is like a vector. So this part is the same for both bases. So it doesn't affect the direction of the spinner. The direction of the spinner is fully dictated by this d guy. Okay, and in this case, we have dx of k is equal to minus t sum over j cos k dot delta, and dy of k is equal to minus t sum over j sine k dot delta. dz is equal to m minus 2t prime sum over j sine of k dot gamma j times sine phi, and the psi of k in our case is minus 2t prime sum over j cos k dot gamma j times cos phi. And then we can, as before, we can also write the eigenvectors. So we can write the eigenvectors u minus of k is going to be 1 over square root of 2 1 plus dz minus dx, and okay, in a moment I'll explain what this is. 1 plus dz hat, and then u plus of k plus dz hat dx hat plus I dy hat, and d hat is equal to d vector over d. So this is the unit vector. And then we have that, for example, u plus minus of k sigma u plus minus of k gives us plus minus d of k. And we also have that e of k, the dispersion, is just, it's psi of k plus minus the absolute value of d. So it's kind of very useful to use this analogy to spin, because we can do all these. So in my notes, I don't know if I can present them here. I don't know. But in my notes, I drew the dispersion. And for example, if you take the flux to be 0 and the mass to be 0, it becomes kind of a particle hole asymmetric version of graphene with 2 Dirac points, one at k and one at k prime. If you turn on the flux, you will open a gap everywhere. And then if you so it's kind of like this. Maybe I'll draw it. We have kind of like a phase diagram where this is like m and this is like the flux.
What's breaking the particle hole symmetry?
What
M
is
equals 0,
breaking the particle hole symmetry? The T prime, the next nearest neighbor copy. So if you want to break particle hole symmetry, you want the positive band to be different from the negative. And you see it here. You see it from the dispersion relation, right? Because the particle hole symmetry comes from the parts that are exactly proportional to sigma. But this part adds to both of them the same. So then you have what the top band is going to be psi k plus dk. The bottom band is going to be the same psi k minus dk. So they're no longer look like mirror images of each other when you take e to minus.
Saying it also in graphene we have next nearest neighbor.
Right, and it breaks the particle hole symmetry.
And it's imperceptible.
First of all, I would argue that it's not imperceptible. example, because indeed, you see this. They do see such symmetries. If you just do a measurement of it's enough to do conductivity as a function of gate voltage, and you see that they don't look the same on the same two sides. No, but they do. Come on, if you look far enough, you will see a difference.
Yeah. Okay. You don't look far enough from the.
Oh,
point.
so
That's
now you're
different.
talking about the Dirac point.
Yeah.
So
That's the only
okay,
point
so
you can
there is a distinction between what we call symmetry and what we call an emergent symmetry. An emergent symmetry is where you don't really have a symmetry, but as you lower the energy, like the symmetry breaking terms become less and less important. Here we're going to have the same thing. So if you focus on the Dirac points, they will look symmetric, close. Okay? But that's never a real symmetry, right? It's a approximation where we neglect symmetry breaking. So, yes.
Why is that next to the value on d hat when you wrote like u sigma vector u? Should be like only d hat, right? No.
Oh, sorry. What am I?
It's a vector, right? Yes. So
Yeah. Sorry.
Okay,
there is
okay,
no.
okay.
Yeah. You're right. This is just the direction.
Oh, okay.
It's a direction.
Yes,
Sorry,
yes.
that was a mistake.
I see.
It's a vector. This is a vector. This is like if you. Oh, sorry. Bad. This is like the pseudo spin magnetization. And then we have two bands. One of them is pointing in one direction. The other one is opposite. Okay. And now we can make. Okay. So first of all, let me pour on you the words first, and then we'll dive into them. Okay. But the point is that what we see here is that, first of all, let me ask you a question. Now we're talking about a Brillouin zone. Before, we had a circle, which was the one-dimensional Brillouin zone, and we mapped it to a circle, which was a vector on the unit circle in 2D. So from a circle to a circle. Now, what is the shape of the Brillouin zone in this case? It's a torus. Okay, everyone understands that the Brillouin zone is a torus? Is there anyone who never thought about this concept? That the Brillouin zone is a torus?
Please assume somebody.
Okay, assume. So the point is that the Brillouin zone is periodic both in Kx and in Ky. So how do we make? So one way to make something, like we can draw a Brillouin zone like this, okay? And then say that, as you cross through here, you come back here. So it's like periodic. You make sure that it's periodic. But a very explicit way of making it periodic is just gluing it to itself. So imagine if I glue this point to itself, then I get a cylinder like this, right? And a cylinder is automatically periodic. So the Brillouin zone, I can think about it as a cylinder in this direction. But then I can also glue this part to this part, so also in the other direction it will be periodic. And then I get the topological structure I get is what you call torus. Luckily, my friend Zohar Ringel taught me how to draw a torus. So this is a torus. Okay. And then, for example, this could be Kx. And then this direction that wraps in this direction could be Ky. So the Brillouin zone is a torus. This vector D lives on what? Sphere. Not just any sphere. We know this sphere, right? It's D. Huh? It's the Bloch sphere. So what we have now, okay, let's call this guy H hat. What we have now is a mapping from the torus to the sphere. Okay? And this mapping, so this is, by the way, these mappings, they're called homotopy groups. And this homotopy group is called the second homotopy group from the torus to the sphere. And in topology, this is known to have a Z invariant. What do I mean by a Z invariant? Let's try and unpack this thing. What?
You're You're losing a hole. Right?
I am losing a hole. What do you
In the
mean?
mapping.
I'm losing a hole in the mapping.
The sphere doesn't have a hole.
Yes, that's true. But I don't think that that's the. Is that a? Well, it has to be essential because, for example, the mapping from the sphere to the sphere is trivial.
Mm-hmm.
Okay.
But you can't.
What?
You can't really map a torus field.
Why not?
And have a correlation from each point to each point because you cannot map the sphere to the Brillouin. It's not making sense.
No, it's not.
No.
It's
So
not any sphere.
No, but anyway, you
At
cannot
each-
take a sphere
at
and map
each
it
point
to
in space.
finite.
no, at each point in space, I assign a vector.
Okay.
Okay. And now I go around the entire Brillouin zone. So I want to see, where this vector is going to point as you go around the entire Brillouin zone. Like the most trivial thing would be, imagine that everywhere like we can always on this Bloch sphere, right? We can assign a vector.
Okay.
This vector is like D.
Okay.
So everywhere, imagine, for example, that everywhere in the Brillouin zone, it's pointing up.
Okay.
So okay, I see what you mean right now.
But you're not projecting, but that's exactly the point. You're not projecting on a sphere, you're projecting on
Yeah.
a sphere with the vector field.
Yes, exactly. So I have a vector field here,
Okay.
which it's a good point. We need to think about how to explain it properly.
But I'm basically arguing that there is at least one point on the sphere that does not exist in the torus. Okay. Has to be at least one point.
No. Okay, that's if you want to map like each point on the torus
Yes.
to a point on the
Right.
sphere. But that's not what we're doing. We're assigning each point on the torus with a vector, and that vector is pointing on the sphere.
Okay.
Okay.
I see the difference.
So maybe this is not a good drawing. But now imagine that as we go around the Brillouin zone, this vector is kind of changing. Okay, so it can basically, and we assume that everything is continuous and smooth, so it can basically cover some sort of area. Okay, and just as before, like I can kind of assign. Maybe I'll just draw it like this. So basically, you could imagine wrappings where, as you go through the entire Brillouin zone, this vector D kind of covers some area. Okay, so that's one type. But then, and this is what we call C equals 0. So this is the trivial mapping. And by the way, it's a trivial mapping because imagine that I change parameters. I could imagine that when I change parameters of the model, maybe the region it covers changes. And I could work in a way to kind of shrink it to 0 without anything abrupt happening. But on the other hand, you could have another situation where this kind of vector, as you go around the entire Brillouin zone, it actually points everywhere on the sphere. Okay, so it kind of wraps completely around the sphere. Okay, so as I go through the Brillouin zone, it starts pointing here, 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 and goes all the way around and covers everything. And then it's kind of like the region it covered is really closing on the sphere. And this I cannot change continuously to this without ripping, how this vector winds around in the Brillouin zone. And so this is C equal to 1. But just as before with the circle, you can have even larger numbers. So imagine, for example, that when you cover half of the Brillouin zone, you cover the sphere already once. And then when in the other half you cover it again. So you cover it twice. So that's again topologically distinct from here. Now I remind you that when we talked about the Mobius strip and the mapping from the circle to the circle, we had a Z classification. It wasn't Z2. What made it Z2 was a gauge invariance that we had. Okay, we could map, you know, different, like all the even Z we can map to the trivial phase, and all the odd Z we could map to the topological. Okay, so now let's talk about the topological invariant in this case, which is known as the Chern number or the TKNN invariant. Okay, so erase this. So just as before we had the Zach phase, also here we have an invariant that allows us to distinguish one kind of band structure from another. So the T here is, by the way, Paulus, who also got the Nobel Prize for the... So the idea is that we can, for each one of these bands, we can define a Chern number, which is 1 over 2 pi integral over the entire Brillouin zone, over an object which is known as Berry curvature. And this Berry curvature is derived from a Berry connection, which is what we call A. You can kind of think of the Berry curvature as a magnetic field in momentum space, and then the Berry connection as being the gauge field from which it derives. And then this Berry connection is very similar to the object we had in the Zach case. Okay. Okay. And then we have U, so this is plus minus. Okay. Okay. So what this guy is telling us is the overlap between a wave function, which we modify by a small k, and itself. So it's telling us something about how this D is changing as we change k. Okay, let me see. Okay, so one important comment. Let's write the comment. So the first one is that this topological invariant also has a consequence. When you are in one topological class and you have a boundary with a vacuum or something, you will again develop edge states. But these edge states have a much more first of all, they're much more robust because they're not protected by any symmetry. Okay? By the way, I forgot to mention, if you remember, I told you that breaking the sublattice symmetry in the SSH model ruins the topological distinction. And you can also convince yourself that it lifts the zero energy states from 0 to a finite value. Here, it's not. This is not protected by any symmetry. So these edge states that we have will remain regardless, okay, and that makes them much more robust. And the most outstanding experimental consequence of this topological invariant is the fact that we have a quantized Hall conductance. So I just want to comment that when the C is non-zero, okay, and when I mean C, I mean summing up all the C's up to the chemical potential, then we're going to have quantum Hall conductivity. So that's one important comment. The second important comment is that you can also identify that this object is somehow related to displacement in real space, right? Because if the operator, the momentum operator in position space is a derivative, right? That means that the position operator in momentum space is also a derivative because they don't commute. So this thing can be viewed somehow as some average position. And just, I don't want to discuss this too much, but there is a concept of topological bands having, the wave functions in real space associated with these bands being shifted and giving rise to some sort of dipole moment. So that's another kind of physical consequence that can be discussed. Now, let us write down an expression for this Berry curvature. So the Berry curvature, if I write down what I just have there, I'm going to have something like this. Okay, now these two cancel. I'm assuming that the order of derivatives doesn't matter. So all we really need is to compute this. Now this I leave as an exercise for you guys. It's going to be one of your exercises. Can be shown, using the expressions we had for the vectors, can be shown to be just given by this. Okay? So it's a very nice mapping between the Berry curvature written in terms of wave functions and this unit vector. Okay? And this is, in fact, if you look at the topological classification of spheres, this is the expression that people use. So basically we arrive at the conclusion that the Chern number is 1 over 4 pi, the integral dkx, dky, d dot d hat dkx cross d hat to dky. Now I want to argue that this integral, okay, will always give you integer multiple of 4 pi. Is it obvious why? Do you see that? Do you feel like...
Wait, is it a...
Sounds like no.
Sounds like not. No, it can be figured out. I'll make a few drawings and maybe we can...
So this is the Jacobian.
This is, it's very similar to a Jacobian. That's one way to think about it, because when you transform to spherical coordinates, then you have, at least for curved coordinates, you get, this is like a determinant.
Yeah, exactly.
This guy is the determinant of d to dkx, dd to dky. So if you take these three vectors as a matrix and you take the determinant, that's the determinant. That's true. Yeah, what is a question or comment? Okay, so let me try and convince you that this is the case. So I'll draw here like a few reference frames. So first we have this vector d, okay, and say this is theta and this is phi. Okay, now imagine, okay, that I have the same d, but I add to it a small dkx. Okay.
Just to be clear, when it said
This
y,
is-
it means ky, the derivative, or does
What?
the derivative in respect to x?
What is x?
Like the coordinate, because you wrote for the omega, you wrote.
You're asking. You're
No,
asking
look,
what this means.
Second line, you wrote.
This.
No, second line, you wrote derivative.
Ah, yeah, that's dkx. Yeah.
Okay, yeah. I thought so, just so it wasn't.
I thought this is an advanced course.
Yeah, but if you change notation halfway through, people are going to be confused.
What?
If you change notation in the middle.
No comment. Okay.
It's like the homework is to keep the notation correct.
Okay. So now let's assume that here this vector here, this guy, is like d hat of k plus dk or some delta k in the x direction. Now similar here. So then we have like a small vector in that direction, which is exactly this derivative, right? Because it's going to be the difference between these two. And then we have a similar. So this is again d of k. Then we could imagine having, some. And let me make this explicit, right? We have some phi here and some theta here, which are different. And here again, we can have this vector, this small vector. This guy can be d of k plus some small delta k in the y direction. Okay? And everything is on the unit sphere. So if I draw the unit sphere, what I actually have, so here I have this vector like d, and then I have these two vectors, like one of them is like here, and the other one is like here, and then this is pointing in that direction, and that is pointing in this direction. So this guy here is like d hat to dky, and this guy here is d hat to dkx. So what you see is that these guys are like they're like these small vectors, and remember that d is pointing outwards, right? D is like a unit vector in the third direction. So they're like an orthogonal system. Okay. By the way, do you know why they have to be orthogonal? That's another thing which it's important to comment, that dkx is equal to 0 and d dot dky is equal to 0, and then you can also prove that so this, maybe I'll also give you in the exercise. It's very easy to prove that. Okay? But basically what this means is that we have three orthogonal vectors. And then this product, as you very well know, because I'm sure you were taught, when you started vector analysis, that this is basically just the volume of the teiva, like a box. Okay? But in one direction, it's proportional to unity. So it's basically the area covered by this small element. So when we do the entire integral, it just gives us the entire area that's covered by this vector on the sphere. Okay? And therefore, by the way, it means that something I said before was incorrect. Sorry. No. Okay. Forget about that. But it gives you the area. Now we have to be careful, because what we're doing is we're integrating over this entire area. And if, for example, the vector is first, imagine that we have some covering which starts from the northern pole and then goes outwards, but then as we complete the circuit around the entire Brillouin zone, it has to go back from periodicity. And as we expand outwards, it's going to give a positive result. But as we go inwards, it's going to cancel out. So anything that doesn't cover the entire sphere is going to give us just 0. The only way we can get 4 pi is if we go over the entire sphere. And each time we go over the entire sphere, we're going to get one factor of 4 pi. So this thing is basically telling us how many times we cover the sphere. That's basically what this invariant is telling us. Okay? How much time do I have? I don't?
No.
So let me finish.
Take 2 minutes.
2 minutes. Okay, so with my 2 minutes that I have left, let me just go back to the model, to the Haldane model, and just give you the two important results regarding this Haldane model. First of all, I want to draw a phase diagram. So we did not calculate anything explicitly. I just showed you how it works, but you can actually make a phase diagram. You can make a phase diagram in the space of phi and m. And it looks something like this. Okay. Where this thing here is 3 times square root of 3 minus 3 square root of 3. These maximum points are at minus pi over 2 and pi over 2. Of course, it is periodic at pi and minus pi again. These lines here, let's call it the dashed lines, are points where the band gap numbers being swapped between the bands. Okay, because it goes from minus 1 to 1. That's an important comment, so you can associate a phase transition between Chern bands with a Z classification as a closing of a Dirac point. Each jump in one unit is a touching of a Dirac point. So and then the last thing I want to comment, which is really hand wavy, but again, I will give it in the exercise, I will make it concrete, is that if we introduce an edge, say we take this model with C equal to 1, okay, say we have a slab, or like an infinite slab, with C equal to 1 here, okay, then we're going to have 2 edge states, one on this side propagating in this direction, and the other on this side propagating in that direction, like a quantum Hall state. And we can see this in the dispersion because it's finite in this direction. So this would be ky. Okay, so I'm plotting it as a function of momentum in this, but in this direction we have a bunch of quantized states. So I can write the different. So I can ky, and then I have some index nx. I can have a bunch of bands, and they're going to look like this. Okay, say this is the k point. So it's generally gapped in the bulk because of this sublattice potential, but then we're going to have like, maybe I'll actually give this a different color, like red. So that means that you go in positive ky direction. Oh, sorry. In positive ky direction, you go on this side. It's the green. So we have one mode that looks like this, and the other mode that looks like this. And these are our edge states, and I will let you derive them in the exercise. Okay, so all this we can do. Okay, from this model. Okay, so that's with that I finish, and thank you for listening. And let's not thank Hanan for his angelity.
מבין איך אנחנו מבינים טופוס או ריבוע סופי להסבר.
לא, אתה לא אמרת אותו, זה לא אחד לאחד.
בוא,
כל נקודה יש לך...
כאילו יש לפחות נקודה אחת בספירה שלא קיימת בריבוע.
לא, יש לך ספירה ווקטור. עושים את הוקטור שאתה רוצה. ויש לך הרבה יותר דרכים למקם את הוקטור שלך מאשר נקודות על הספירה. זה כל ספירה, כל נקודה
אפילו עוד יותר טוב.
לא, זה לא מיפוי אחד לאחד.
לא, אבל גם אם זה לא מיפוי אחד לאחד, כאילו לא יכול להיות שבכל נקודה ספירה, נקודה קורלטיבית בריבוע.
יכול להיות שאתה צודק שיש סינגולריות.
יש סינגולריות?
כן, יש אחד.
כן, לא יודע.